everyone, my name is Wen Xu and I'm a PhD student at Northeastern University. Today I'm going to talk about my work with Dr. Padilla on shifting expectations for encoding rules mitigates misinterpretation of connected scatterplots. In this work, we're looking at connected scatterplots. These are visualizations that data journalists often use to tell the story of how two variables change over time. More specifically, it is a scatterplot where each data point represents one specific time point, and all of them are connected by a line that follows this time sequence. But sometimes it can be a bit difficult to interpret these plots. For example, let's say we are trying to figure out how did the y variable on the highlighted line segment here change over time. Many viewers might say that y increased, but the correct answer is actually that y decreased from 2008 to 2009. So why do people misinterpret the direction of time in connected scatterplots? In this work, we are proposing a perspective to understand this error based on a concept called expectations. Expectations are the initial and intuitive assumptions that people have about the encoding rules in a visualization. For example, in a Cartesian plane, we might expect higher values to be represented by higher positions on the y-axis. In a map, we might expect higher positions to represent northern regions instead. And we might expect warmer colors to represent warmer temperatures. And we speculate that people misinterpret connected scatterplots because they violate some viewers' expectations about how time is encoded. More specifically, because these plots look very much like a line chart, viewers might expect it to encode time from left to right across the x-axis, and let's call it the right is later rule. So if people expect the right is later rule, they would say that y increased in this line segment because it went up from left to right. But the correct rule to use to interpret these plots is actually that time follows the line connecting the points, so it doesn't always go from left to right. So since this misinterpretation is likely caused by this misalignment of expectations, we wondered if we can mitigate this error by shifting viewers' expectations to align with the correct encoding rule of the visualization. We conducted 3 pre-registered experiments to test this idea. In experiments 1 and 2, we looked at 2 different strategies to shift people's expectations of how time is encoded in connected scatterplots. In experiment 3, we applied these strategies to more realistic connected scatterplots to see if they actually increase people's accuracy in understanding the data in these visualizations. Because we're interested in people's very initial expectations for encoding rules without any influence of the textual information like labels or legends in the visualization, in experiments 1 and 2, we designed a task to elicit those expectations. So we showed people this graph without any labels or legends, and we told them that this point on the left marks the first year in the dataset. Then we asked them which of these highlighted points represents a later year than the other based on their intuition. So if the viewer expected right is later, they would say the point on the right is the later point. If they expected time is a line instead, they would say the other point that is further along the line is later. In experiment 1, we hypothesized that changing people's chart type schemas will shift expectations. And by chart type schemas, we mean people's mental models of different types of charts, including how they look like and the rules that govern them. For example, this chart looks like a line chart, so this would activate a line chart schema in people's minds. And this will lead people to expect the right is later rule very strongly because it is part of their schema for line charts. But if we take the same chart and remove its axis, and also change the style of the line so it's thicker, curvier, and also less opaque, now it looks much less like a line chart, and now people's chart type schema will be unknown, and this will lead them to expect the right is later rule less strongly. Looking at our results, we did find that when looking at the less line chart-like graph, more people said it's something that's other than a line chart, and also more people expected to follow the time is a line rule over the right is later rule. In experiment 2, we looked at a different strategy to shift expectations, and that is through visual cues that indicate direction along the line. And one example is arrows. So if we add arrows to the connected lines, this will strengthen the expectation that time actually follows direction of the line. We looked at 3 different ways to indicate direction: the arrows, a line effect that looks like the point is moving over time and leaving a trace behind it, and an animation that reveals the data points over time. And we found that the arrows was the most effective in increasing the time misaligned expectation, probably because it's the most explicit cue out of the three. Finally, in experiment 3, we showed people more realistic connected scatter plots with more complex data sets and measured their accuracy in understanding the data behind these visualizations. For example, we'd ask them, how did the price of a gallon of gasoline, so that is the Y variable right here, change over time in the highlighted region? And the participants can either select it increased or decreased. We used 2 data sets, both replicated from existing connected scatter plots, and we asked people for the trend of the X and the Y variable in 4 distinct regions in each dataset, and these regions covered all the possible line orientations and time directions in the dataset. We tested 3 individual interventions from the previous experiments, so that is downplaying the line chart schema by removing the axis and changing the line style to a more atypical one. We tested 3 individual interventions from previous experiments, so that is downplaying the line chart schema by removing the axis and changing the line style, the trace line effect, and the arrows. And because we found that arrows was the most effective directional cue from experiment 2, we additionally tested 3 conditions that combined arrows with downplaying the schema, the trace, and animation, so that we can see if combined interventions can provide additional benefits. Now let's go through our takeaways from this experiment. So we're looking at accuracy on the x-axis, and we're looking at the regions in the visualization where time goes from right to left. So that is when it violates people's expectations of right is later. And we see that the baseline condition without any intervention led to an accuracy of about 50%. And first we compared the 3 individual interventions against the baseline. We found that downplaying the line chart schema didn't improve accuracy, but both the trace and the arrow, so the directional cues, did increase accuracy. Then we compared within the directional cues, and we found that arrows were more effective than trace. And it produced an accuracy of about 70%, so that's a 20% improvement from baseline. Finally, we looked at the 3 combined interventions, and we found that all of them produced higher accuracy than the baseline. But more importantly, arrow plus trace and arrow plus animation further increased accuracy compared to arrows. So that means redundantly encoding direction with 2 different channels is more effective than just using 1 channel. And here is a summary of all of our results. In this work, we demonstrate that understanding people's expectations for encoding rules can help inform design interventions that can make visualizations more interpretable. There are many other visualizations out there in the world that might similarly violate people's expectations, and we hope that this work can serve as a provocation for more future research to use expectations as a lens to examine and redesign these visualizations that challenge interpretability. Thank you so much for watching. If you want to learn more about this paper, please check out the description of this video.